Welcome to this talk on from text to boxes and how the front end parses in typesets math. So this talk will explain why the front end represents mathematical structures or typeset structures in the way that it does and how the box system supports that representation. So box expressions that represent the mathematical notation in the front end are in a sense prelexed and pre-parsed, and we'll talk about what that means. I'll go on to show how to transform textual math or near math input into boxes via the ReparseBoxStructurePacket. Then we'll go through a simple example, a toy example of this conversion from text to boxes for a domain-specific language. We've just sort of made it up, but it serves a good purpose. It's for illustration. And then for completeness, we'll then move on to covering how the typeset engine interprets and represents these kinds of underlying boxes and how to customize that behavior with MakeExpression and MakeBoxes rules. So in detail, we'll cover the boxes and the representation of typeset structures, the front-end parser and how it canonicalizes boxes, the ReparseBoxStructurePacket and how to use it, a toy example using the ReparseBoxStructurePacket, and then the MakeBoxes and MakeExpression rules and an example of how these things work. A quick example. So a bit of housekeeping as well. There aren't 25 slides. If you take a look at this, there are only 8, but I've included further slides from previous conferences and other reference material in this notebook so that when you download it, which you'll be able to do later, then you can sort of see further sort of examples and illustrations of underlying box technology. And furthermore, I'm going to be switching from slide to slide with different magnifications to whatever sort of best fits the thing that I'm trying to illustrate. Okay. Now I'd like to talk about the nature of the typeset expression in Mathematica, and it all turns out it's boxes, as the front end talks about them. So let's enter in just a simple sort of expression here, x cubed plus 4 minus 2, and we can evaluate that, and it evaluates as you'd normally expect. It gives 2 plus x cubed. Okay, that's great. So what went on? So we sort of typed in some sort of text string, which is sort of the characters, x, some sort of power character, a plus and a 4 and a minus 2. But yet the front end actually represents that slightly differently. It represents these as boxes. And so if I copy that expression and I paste it again, so we can see the exact same typeset structure on 2 lines, and on one of the lines we're going to take a look at the underlying structure here. So I've got the cell bracket extended. I could be anywhere in the cell. I could copy an expression. I could select an expression here, and I go show expression, and we see that this typeset structure, x cubed plus 4 minus 2, is represented by these boxes. So this x cubed is actually internally represented by this superscript box. And so this Command-Shift-E here, I'm going to toggle this back and forth. You can sort of see it's represented. I could go in here and change that to a 4 or whatever, toggle that back, and then change that back to a 3 if we wanted, and so on. Okay, so the boxes here are represented, this represents the superscript box here. We have these separate, that's being broken up into tokens, the plus 4, the minus, and the 2. It's not just a single sort of string of plus 4 minus 2, it's this whole sort of broken up tokenized thing. And in fact, if we go here and we get this and we actually sort of change the boxes, we could reformat that, and it sort of works. It even evaluates. To something a little bit weird. So it doesn't quite do the right thing here. We've got 2 plus x, 2 times x cubed, but which instead of that should be 2 plus x cubed here. But so what went on? So I think this thing, what it evaluates to, that evaluates as a single token, and it by changing these boxes underneath here, we've got some sort of weirdo thing here, and it's changed it a little bit. But of course, what we could do by hitting a plus sign here is just reparse it completely, and you'll see that it changed that spacing, and now we've seen it change back. So it does this reparse, and so the boxes, when they're slightly malformed or slightly corrupted, they sort of reparse themselves and work themselves into a different form. And we're going to talk about that in the future as this talk coming up. So and of course, these boxes are well understood by the kernel. There's this mechanism as we shift them off to the kernel. Of course, these things become, this whole expression is an interpreted plus of power x cubed, comma 4 minus 2. Okay, so the kernel, there's a way when it sends off boxes off to the to the kernel, it uses MakeExpression there for the kernel to interpret them, and likewise to get boxes back from the kernel, it uses MakeBoxes. And we'll talk about those in a second. But the important thing here is to recognize that these are boxes. They're correctly structured and broken up, sort of tokenized. And of course, this works for much more complicated things. If I get some integral infinity here, and we get some, exponential e to the minus x squared here, we're getting some sort of Gaussian here. We get this square root of pi over 2. And of course, I'm going to use the same trick as before. Take a look at this, and now I go and I take a look at this show expression here, and I take a look there, and I see this underlying form here. Again, I see that form right there. So, and we see that the integral part is represented by this subsuperscript box of integral 0 to infinity. We see the next part here, this superscript box. Right there is this exponential e to the minus x squared. That's that part right here. Row box minus superscript box. And of course, there's this row box differential d. And of course, these boxes have to be in the right sort of structures we saw. If we sort of malform them here, underneath, by going in and altering the boxes, we get different sort of results. And of course, even if we don't malform the actual boxes ourselves, we use the Mathematica typesetting editor, and we enter something else like this. This doesn't make sense in this current. It doesn't have any parsing rules for that the way we typeset that, and so that's an error, of course. And so we have to know the correct form of this. And if we don't know that, we can of course enter in through the basic math assistant. You could go here to advanced and type it in, 0 to infinity of, you could use the palette again. I'm a bit faster than using the palette here because I've used Mathematica for so long, but of course you know that this is the sort of structured form that this is put in. Of course, TemplateBoxes will make this even more strict and more enforced, but we'll talk about those a little bit later on. But the important point is here to recognize that these boxes are the things that represent these typeset structures. There's many, many boxes in Mathematica. We add new boxes all the time. But for the basic math things of powers and subscripts and superscripts and fractions and some of the other things, they're a very fixed sort of collection of boxes. Okay, so I want to talk now about how the actual parser works in Mathematica. Okay, now I'd like to talk about the front-end parser. And to do this, I'm going to evaluate these expressions here. So we've got this one variable, the boxes, and we're creating an input field where this is changing, and the input field will record its contents as boxes, and it'll do that continuously. And now we can take a look at the output of that, of what is the boxes at each point in time, and we're going to show the string characters. And so now if we type something like x to the power of 3, we see, as our previous example, we see this superscript box, and now as I type plus, we see this row box starting to group it. We type a 4 and then a -2, and we see now the exact same structure we saw in our first example on the previous slide. So as we type these expressions here, the structure groups and it breaks it up, these characters, into boxes to represent the underlying things that we type. And so let's go a little bit slower here, and let's take a look at some tokens. XXX plus YYY times ZZZ. Okay, so what's actually happened here? So normally in any sort of compiler here, we've given a sort of string of tokens. We're given a stream of tokens, XXX plus YYY times ZZZ. Or a stream of characters, actually. And so what the lexer will do in any sort of compiler here, it'll break this up into an XXX and the plus token. It's going to be tokenizing this and breaking this all into tokens. And so we'll get this stream of tokens here, the times token and the ZZZ here. Okay, so that tokenizes it, but moreover, we've seen it actually structures it. It groups this together. There's a row box around these particular things. So not only is it sort of tokenized it, it's turned around and it's sort of parsed it into this. It's grouped it according to the precedence of the times here. And we'll talk about how you can. Mathematics has got its own internal notions of precedence, but time permitting, we'll talk about how you can alter this with syntax form for tag boxes and template boxes. Okay, so this expression here is now pre-lexed and pre-sort of parsed. And of course, this works for more complicated expressions here. So if I go back to the more complicated example I had before at the beginning, on the other previous slide as well. And as I type this, we now see that's a sub-superscript box. And now if I put this exponential e in here, minus x, squared dx, as I type this, we see that the front-end parser is actually going through and it's changing these boxes, and it's creating and destroying and munging these boxes into a new box as we type characters. And that's the role of the parser, the incremental front-end parser, the box parser, which works with these particular tokens. Okay, so the next question and the next slide is how we can actually do this ourselves, take text strings, as we saw where they're sort of malformed, and get our own boxes. And so instead of actually typing them directly into the front end, how can we get the functionality of the front end to do it for us? Okay, let's talk about this process of reparsing boxes. So instead of actually having to type in to the Mathematica front end various inputs to actually get it to reparse, we can reparse with the packet. And so I'm just going to create this shortcut. We're going to reparse of some various arguments. It's just going to be mathlink calling the front end of this box structure, the ReparseBoxStructurePacket. So now that we've got this, we can actually go ahead and reparse things. So one of the things we might want to reparse is just our simple string that we had from before, xxx plus yy, and then times zzz. And we can see if we do this, now we get the correct structure. And of course, this is an output, and in an output form, the string characters are not shown. So if I just select the output line and hit a space, it creates an input line, puts it into the input style. As we see from here, it's an input. It's changed it. We could, of course, just get the output and show string characters here on that to turn that on. And so we could actually sort of see show string characters in the output. But I can just select the output and then hit the space bar, and it'll make it an input, and then we can see the structure. So here, when we reparse this string, we can see it's actually gone ahead and lexed it. It's broken it up into tokens, and it's grouped it accordingly. And so it's created this actual box structure. And so, of course, this doesn't work just on strings. We can go back and we can capture this particular expression here, which was we worked with it, which was malformed. If we go in here, this box structure here, let's go in and malform this, reparse. We're going to get this structure, and we're going to change this to plus 4 minus 2. And so it's got a box in there, plus it's got some actual text in there, and we'll reparse that. And that, likewise, just as before, we'll turn around and clean this up. So this reparse here will actually go through the structure and reparse things. And it's just like typing in to Mathematica, the front end, and cleaning it up that way. There's another option to the ReparseBoxStructurePacket, which is stripping boxes. And so sometimes if we've got things like a style box around some sort of structure, and so we'll go here and we'll get around this particular output here, and we're going to make that font slant goes to italic, for instance. Okay, so when we do this, we see that it's actually stripped it hasn't stripped the style box here, and we've got this whole thing here is it's reparsed this, because this is acting like if we reparse just the front bit, we see it's reparsed as a plus 4 and minus 2. And it hasn't put this all into one sort of line because the style box has sort of grouped it around there. We could actually turn around and go strip the ReparsePacket there, and turn around and strip boxes. That's right, goes to true, and turn around, and this will now strip out the style box, but we can actually sort of see that it still hasn't fully flattened this. And so in the one parse, because strip style box happens a little bit later on in the process, and so sometimes you might want to even reparse that again, and then finally doing that, we can actually get back to cleaning it up. So sometimes you might need to call this more than once to actually, depending on your particular application, get this and actually clean up the various structures. Okay, let's work with the toy example now. And so what happens when we do some taking in some text from outside Mathematica, the front end, and bringing it in to boxes? Well, what happens is we normally start out with some text here, and then we'll probably do some string replacements on that, and then from there we'll turn around and actually do the reparsing once we've got it in some particular form that we want, and then finally from there we'll probably actually do some box replacements on that. And so that's the sort of process we would normally do. And of course there's many other things that we actually bring into Mathematica, like MathML or HTML, LaTeX, for instance, and Markdown is some of the various things. So there's many other languages out there that are sort of markup languages in one form or another, and we want to get that text into Mathematica in a form of boxes that we can actually work with. So let's consider some small example here. So let's try and turn around and reparse, and we're going to reparse some expression. And so that'll be, there's some mathy bits to it really, and then there's some operator. It's got the com operator, and then it might be nested, B, C. Okay, so reparse will take that and will give us some sort of box structure that's fine, and we can take a look at that in raw boxes, and then we can try and evaluate that, and we find out, well, that doesn't evaluate. And of course, because a com of A, comma B, that thing there, it won't work. We need some square brackets around the commutator to actually work. So what we need to do is we need to do that replacement. So this thing here needs to basically go to this thing here, but for the boxes. And so we go say, well, what are these kinds of boxes that are around? It looks like that. And in fact, if we took a look here, we'd sort of see there's the com operator that we've got. So we need to define some sort of operator here, which is my replacements of some expression here is equal to E / dot. We'll do it repeatedly. So / dot. And so we're going to look for something else like this, and we're going to take that. We'll make that a general argument, and we're going to get this other general argument, B underscore, and so we're going to replace it by basically itself, except for, this is now, so that would be the identity operator, but we're going to change these round parens into brackets. And so now we can apply that in the actual chain here, and we get down to something that's looking a little bit better. It's almost something we can use. We try and evaluate that. It doesn't quite work, and you can sort of see that operator here, there's a little bit, the spacing is just a little off here. And that's because this com of B, C here, it's represented as something like this, where we see this paren here, the com, and then a bracket. And if we take a look at this thing here, we don't actually see that. We see this com and the brackets on the next line. So it's not quite in the right form because of replacements. And so what we can actually do is turn around and reparse that. And then finally, and that'll clean up the box structure. It's the same as if we didn't have that, and we went in here and actually typed the characters around that operator again here to make that actually reparse. Right. So that wasn't. It's not in the correct form here. We could change this rule to make this rule a little bit better to clean it up, but this is an example here. We could actually just turn around and use the ReparsePacket again on our semi-malformed boxes, and now this thing will actually evaluate. And of course, we could turn around with this replacement rule that we have right here. We could actually turn around and make better replacements too. And instead of this structure here, this could actually be a template box, for instance, of the arguments A, B, and we give it an operator. And I've actually built this into the style sheet. Commutator, something else like that. And now this replacement, replacement 2, looks like we'd expect. Looks kind of nice, and it has the template argument, so you can tab around, and it evaluates. Okay, so that's just a simple toy example showing the sort of process of where we possibly use reparsing and into various structures to facilitate this translations from strings or some domain-specific language into Mathematica boxes that we can actually turn around and further use. Okay, I wanted to quickly talk about box generators and graphics boxes. And so if I evaluate a normal graphics expression, you can actually see that underneath, I'm doing this Command-Shift-D, we see it's made up of a graphics box of a line box. And similarly, if we get a Bezier curve here, we actually we generate this graphics of a Bezier curve. It's actually a graphics box of a Bezier curve box. And similarly with all controls, we have a style here, and that as we generate, we use as a generator, this generates a style box with strip on input, goes to false. And similarly here, a button will generate a button box, as we see. Click on it. A slider will generate, this box generator will generate a slider box, and as we change it, and of course a dynamic will generate, if we take a look at it, a dynamic box. And now these things are linked as I change the number, the factorization, and so on. Okay. So basically, underneath, everything is a box. It's all about boxes. Okay, after covering typeset structures in Mathematica in the front end, and their underlying representation in terms of boxes, and the front-end parser and its actions, and how it cleans expressions up, it canonicalizes the underlying boxes, and of course the reparsing to do that, it's important for this discussion to at least cover MakeBoxes and MakeExpression, and one example from this. So how do these boxes that we've been working with, how do they work with the kernel? How does evaluation occur? Well, if I take some expression, here's the partial derivative of sine y over 2, we get cosine y over 2. It's, derivative of sine is cosine. Everybody should be happy with that. But the sine, this expression here, this typeset expression, as we know before, it's represented underneath by some boxes. And which boxes are they? Well, there's the subscript box of a partial d fraction of blah, 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 this fraction box of the sine y over 2. And of course, the output is represented by boxes as well. It's a fraction box of cosine y over 2. So what actually happens? How does this evaluation take place? Well, we start off in the front end with this nice typeset structure. We have partial y of sine y over 2, but that's represented internally, as we've just seen, and as we know here now, by boxes in the front end. So we have this set of boxes. And so with these boxes, we need now to go through parsing, which is MakeExpression, to get to a kernel expression. And the kernel expression is represented by something like d sine y over 2, with respect to y, the derivative of that. And of course, the kernel can actually handle this. This is normal kernel evaluation with normal calculus rules, and the derivative is sine is cosine, and we get a new kernel expression. And now we need from that new kernel expression, or the resulting kernel expression, we need to get a set of boxes. And so it goes through MakeBoxes, and so this gets made into these boxes here, and those boxes are now displayed in the front end as cosine y over 2, and of course that's now how we perceive the evaluation to go from this typeset answer to this. That's how evaluation works. So now let's see this in action. So I've gone and I've changed the evaluator here to link snooper, and I've set it up. So I've spun it up, warmed it up, and so we can see that particular result. And let's go see what happened in link snooper. It produced this particular result here. And so if we go off to here and paste that in, we see that the front end is sending off to the kernel this expression, MakeExpression of this particular thing. This is the partial character here. The partial of y of the fraction box of row box sine y over 2, and the kernel responds back to the front end, hey, here's this, it's result 2's coming, and here is the result here. It's this box data fraction box of this row box cosine y over 2. So we've sent the front end has sent some stuff off to the kernel, and the kernel's actually returned with results, and then and that's through MakeExpression, and the kernel internally is given us these results through MakeBoxes, and then we display them in the front end as we see visually here. So let's quickly illustrate this MakeExpression and MakeBoxes rule by one example here. Here's a made-up example for partial plus of some argument here, and it doesn't currently parse in Mathematica because there's no rule for being able to handle that. Mathematica doesn't know how to make that and make that into an expression. So what we're going to do is we're going to add our own MakeExpression rule for these particular boxes in standard form. And that's going to be equal to, which boxes will it be equal to? Well, it'll be equal to these boxes here. So we go here, grab that, and make expression of those boxes in standard form. So Mathematica doesn't know how to do the stuff on the left-hand side, but it knows how to do the stuff on the right. And of course, this is for any argument here. So we just put that in here like that. Okay, so that now tells Mathematica how to be able to interpret the boxes and now how to format them. Well, we need a MakeBoxes rule for this, and so which boxes we're going to make this thing here in standard form into some boxes, and which boxes it's going to be. Well, it's going to be these boxes here that we've just done, and of course this result here, we need to make that again. And so that's just a V right there. And so that's now the two rules we have. And now we can define like a linearity rule with that and do some calculations. PD plus, let me put a underscore there. There we go. PD plus, and so on. And so full form of percent, it does the right sort of thing as we'd expect. So it's got the right internal form in the kernel, and we've told how to interpret these particular boxes that match these things, and how to format through MakeBoxes things that are internally represented by PD+. So on to the final conclusions. I blasted through those last points in terms of the MakeExpression MakeBoxes and of course the example in a very quick fashion. It gives you a taste of what we can do and the power, the awesome power of being able to override the rules, the MakeExpression and MakeBoxes rules for Mathematica, and bend the front end and the whole system to your will, and you can change it to do what you want it to do. Okay, so I would highlight as well that in the end the technology has evolved, and so I haven't really talked too much about template boxes. I just used them briefly as one example there, but now that you've got this primer for a lot of how boxes work, how reparsing works, and how the front end sort of structures and canonicalizes these boxes, it would be good to then progress on to actually talking about template boxes. I added template boxes to the front end in version 8, and since then they're now the standard way to do much of the typesetting, much of the advanced typesetting that occurs in the front end, and you'll see them throughout the whole system in a myriad of different ways. However, the ReparseBoxStructurePacket will not actually change any template box structures because the template box structures are already highly structured already in a templated way. If you'd like to know more and explore it, and I find it, of course, I wrote a good bit of it, and I'm intimately familiar with it, and I work with it day to day. But I would suggest you take a look at the advanced typesetting talk I gave in 2021 for the Wolfram Technology Conference, and you'll learn a lot more on template boxes, tag boxes, MakeExpression, MakeBoxes rules, precedences, and some other stuff. And I've linked the videos and the actual download notebook, and also very importantly, Itai Segev will be talking about template boxes and other box concepts. He works more on the kernel. Well, he works on the kernel side. I work on the front end side, along with my other colleagues, Lou and John and lots of other people on these and related concepts. And he'll be talking about template boxes and other box concepts in a hands-on introduction to formula typesetting. And that's this Friday, the 7th of November, as towards the end of this particular conference. And I'd also encourage you to take a look at other related talks, John, Lou's, James, and Yusu's. But now let's just go back and summarize the key points of this talk are that the front end parser built into as you type stuff, it will canonicalize and shuffle and shift boxes around to make them put them into a canonical form, and it does that in the front end. And you can use the ReparseBoxStructurePacket to reparse and canonicalize boxes in the exact same way that the front end does. It runs through the exact same code paths. And you can cause sometimes when you're working with boxes and they get, quote, quote, get corrupted, you've done something, you've edited the boxes by hand, you've put something in, you can sometimes get around it by causing a reparse, by adding a space and deleting it, by shifting it, making the parser kick in and actually make some changes to it. And of course, one of the other key findings and the key points is that you can actually go and change the behavior of Mathematica by adding your own interpretation and formatting of boxes through new MakeExpression and MakeBoxes rules. Okay. I hope you enjoyed this talk, and on to the further talks to the conference. Okay.